As always, read the question first. So we need to know the slope of this graph in order to find the acceleration. Remember, if we think of slope as rise over run, then the rise is the change in velocity, and the run is the change in time. So you can see that the rise over the run is the acceleration. Now, as for which points to use to calculate the slope, I usually recommend the first and last points. And that will still work in this case, but there are a few other good points you can use on this one. So it looks like the point 110 goes right through the grid, and then over here the point 8 and 22.5. I chose that one because it's exactly halfway. You can usually tell when they're right halfway exactly. Now another point that you might have chosen would be 415, but let's zoom in a little bit on 415. You can see that it's not exactly through the grid, and another reason we wouldn't want to use that one is it's a little close to our other points over here. So this point and this point are far enough apart. Those would be two good points to use. I leave it to you to calculate the slope. Example 2, read the question first. So we need to know that on a velocity versus time graph, the area under a graph gives us the displacement. Notice also that we're looking for the displacement only from 0 to 6 seconds. So we're looking for the area of this triangle. Since area is 1/2 base times height, we have the area of that triangle is 1/2 times 6 seconds, the base of it, times, looks like about 36 meters per second, the height. Be sure to notice the units. When we multiply 6 times 36, the seconds will cancel, and so we'll end up with meters, which are the desired units. I leave it to you to find the displacement. Okay, example 3, read the question. Now think about what's different about this one. I noticed two things. First, this one has negative velocities. That means we're going to be looking in this area for our triangle. It's always between the line and the time axis, which in this case is up here. Second, notice this one is different because it gave us the change in velocity instead of the time interval. Since it said 0 to negative 25 meters per second, we're looking for the area of this triangle. I leave it to you to find the displacement on this one. Last one, read the question. Be careful, again on this one, we're in the negative velocity range, so we're looking over here for our displacement. Now the trouble on this one is that it's not just a triangle, but a nice way to look at it is as a rectangle and a triangle stuck together. Let's imagine the object continues at its initial negative 50 meters per second for the full 10 seconds. Then we'd be finding the area, to get the displacement, we'd be finding the area of this rectangle. Well, that one is just negative 50 meters per second times 10 seconds, and we get negative 500 meters. Okay, back to the graph. We still have a triangle left over. So let's look at what our triangle is. That's this triangle here. So we can find the area of our triangle by doing 1/2 the base, which is 10 seconds, times the height, which is negative 30 meters per second, and we get negative 150 meters. Combining those, our total displacement is negative 650 meters. Now, if you were unsure where I got the negative 30 meters per second, we'll look back at the graph real quick, and just remember that I got that by doing negative 80 here minus negative 50 here.